G'day viewers. In this episode we shall take a deep dive into what we have identified as being the cosmic acceleration problem. Although it seems to have been missed by the standard model of cosmology because nobody is talking about it, but multiple estimates from authoritative sources exist which clearly contradict each other with respect to when cosmological expansion commenced accelerating. One source claims it started when the universe was approximately 7.7 billion years old. Another source claims it started when the universe was approximately 9 billion years old. And yet another source claims it started when the universe was approximately 10 billion years old. Hence, the standard model of cosmology is in conflict with itself. So which one is correct? Well, this is what we're going to investigate. On our journey, in addition to what I've already mentioned, we will learn the following 5 points. Number 1, baryonic matter commenced cosmic acceleration at a different instance to the commencement of space-time manifold cosmic acceleration. Number 2, baryonic matter experienced 2 instances of change in cosmic acceleration. The most recent instance results in the cosmic acceleration we measure today via the cosmic distance ladder Hubble constant, h0. Number 3, the space-time manifold has experienced only 1 instance of change in cosmic acceleration. In other words, the space-time manifold commenced cosmic acceleration during the cosmic inflationary period and is revealed by the measurement of the power spectrum Hubble constant, h5. Number 4, the origin of the Hubble tension is tied to the origin of the cosmic acceleration problem. However, the influence of cosmic acceleration is not the only contribution to the Hubble tension. Other contributions exist, which have been discussed in previous episodes. Number 5, our proposition of baryonic matter and the space-time manifold experiencing different manifestations of cosmic acceleration is evident in the standard model of cosmology need for the existence of the cosmic inflationary period. That is, the period when the cosmic space-time manifold expanded at many times greater than the speed of light. Thus, a precedent for our proposition already exists within the standard model of cosmology. Okay, let's begin our adventure. In this illustration, we see the dark energy density parameter plotted by the red curve, the pressureless matter parameter plotted by the blue curve, and the deceleration parameter plotted by the magenta curve. The particle data group estimate for the commencement of cosmological acceleration is represented by the red circle. The US Department of Energy estimate is represented by the black circle, and the Fermilab estimate is represented by the magenta circle. Therefore, according to the electrogravimagnetic construct, the particle data group solution actually denotes the cosmological instant when the dark energy density parameter equals 0. Moreover, the US Department of Energy solution actually denotes the cosmological instant when the dark energy density parameter equaled the deceleration parameter. In addition, the Fermilab solution actually denotes the cosmological instant when the deceleration parameter equaled 0. Since the standard model of cosmology lacks accuracy in the early moments of the universe, the standard model of cosmology relies upon the deceleration parameter to quantify cosmological acceleration. The problem with this is that the standard model of cosmology is insufficiently mature to precisely describe the complete history of the deceleration parameter, particularly in the early moments of the universe. Nor does the standard model of cosmology possess the required level of maturity to relate the deceleration parameter to the Hubble constant, unlike the electrogravimagnetic construct. Thus, we may utilize the electrogravimagnetic construct to compute the value of deceleration parameter in the early moments of the universe. When we do this, we find that the deceleration parameter transitioned from negative to positive at approximately t1. This reinforces the claim regarding the commencement of cosmological acceleration asserted in previous episodes. At this juncture, we will reiterate that the standard model of cosmology does not relate Hubble constant to deceleration parameter over the full lifetime of the universe, as does the electrogravimagnetic construct. Having said this, we must acknowledge that the Fermilab estimate for the commencement of cosmological acceleration is correct in relation to the deceleration parameter, but incomplete. A more accurate description is that the Fermilab estimate is the correct value of the second instance of cosmological acceleration, based upon deceleration parameter. However, in relation to the Hubble constant, the Fermilab estimate for the commencement of cosmological acceleration is incorrect. So, what does all this mean? Well, it means that the universe has undergone two instances of cosmological acceleration. The first instance occurred immediately after the Big Bang, whilst the second instance occurred at a cosmological age of approximately 9.6 gigayears. Thus, the Particle Data Group and US Department of Energy estimates are evidence of cosmological events, but not cosmological acceleration. Hence, the cosmological acceleration problem which we have identified. Please note that all of the information required to replicate the results communicated in this video presentation appear on screen. Please take the time to study the information provided. Okay, let's now walk through the foundations of the illustration step by step. The first feature we shall identify is the EGM deceleration parameter plotted by the brown curve. The second feature is the SMOC dark energy density parameter plotted by the red curve. The third feature is the SMOC pressureless matter parameter plotted by the blue curve. The fourth feature is the SMOC deceleration parameter plotted by the magenta curve. The fifth feature is the EGM total density parameter plotted by the black curve. So then, what is the difference between the EGM and SMOC curves? In other words, what is the difference between the EGM deceleration parameter and the SMOC deceleration parameter? Well, in order to answer these questions, we need to understand how all of these parameters hang together within the EGM construct. To start with, we shall discuss the EGM total density parameter and the EGM deceleration parameter. The EGM total density parameter is constrained by the experimental observation that the expansion geometry of the universe appears to be flat, according to our most sensitive instrumentation. Subsequently, if we consider very small units of cosmological expansion time, say minutes, hours or days, then we may approximate cosmological expansion to be static, simply because its expansion is beyond the resolution of our instrumentation over such short periods of cosmological time. Consequently, the EGM deceleration parameter is trivially derived in accordance with the equation shown. In other words, the relationship between the EGM total density parameter and the EGM deceleration parameter represents the Newtonian balance between two opposing forces, that is, the cosmological expansion force initiated by the Big Bang and the expected cosmological contraction force arising from gravitational effects. In order to get the SMOC parameter curves, we simply break down the EGM deceleration parameter into its constituent SMOC parts, namely the dark energy density parameter plotted by the red curve, the pressureless matter parameter plotted by the blue curve, and the deceleration parameter plotted by the magenta curve. The sixth feature on the illustration is the time constant, the Big Bang Hubble constant, and the cosmological history of the cosmological constant. Let's now declutter the illustration and look at the seventh feature. As emphasized by the rounded box in the right-hand corner of the slide, you see the present epoch values of numerous SMOC metrics derived via the EGM construct. The eighth and final feature on the illustration is emphasized by the rounded box appearing in the lower third of the slide. This contains a great deal of self-evident results, so please pause the video and study the information provided. Okay, now that we have walked through the illustration and explained its constitution in some detail, let's have a look at what the SMOC parameters were doing in the primordial epoch compared to the present epoch. On the left-hand side of the slide, we see the SMOC behaviour of the dark energy density parameter plotted by the red curve, the pressureless matter parameter plotted by the blue curve, and the deceleration parameter plotted by the magenta curve. All of these parameters are plotted for the first fractions of a second after the Big Bang, as numerically indicated on screen. The magnitudes of the parameters rise until their maximum values at 2t phi rho. The instant at 2t phi rho denotes the cessation of the cosmological inflationary period. In other words, cosmological inflation ended at 2t phi rho. On the right-hand side, we see the SMOC behaviour of the dark energy density parameter plotted by the red curve, the pressureless matter parameter plotted by the blue curve, and the deceleration parameter plotted by the magenta curve, from a cosmological age of 3.6 gigayears to the Hubble age of 14.6 gigayears. Please note that the SMOC pressureless matter parameter plotted by the blue curve is always positive. However, the SMOC dark energy density parameter plotted by the red curve and the SMOC deceleration parameter plotted by the magenta curve transition from negative to positive values and vice versa respectively, as indicated. Please pause the video and study the information provided. Okay, let's now zoom in on the instant of the Big Bang. Appearing on screen are two graphical depictions of SMOC cosmological parameters during the primordial epoch. On the left-hand side of the slide, you can see the colour-coded instances where the dark energy density parameter plotted by the red curve and the deceleration parameter plotted by the magenta curve change sign by crossing the x-axis. The moment when the deceleration parameter changes sign denotes the first instance involving cosmological acceleration. That is, from the instant of the Big Bang at T alpha to T alpha Q, the deceleration parameter was negative, which means that cosmological expansion was accelerating. Then, at T alpha Q, cosmological expansion commenced decelerating. Moreover, both of these events occurred during the cosmological inflationary period. On the right-hand side of the slide, you see the same graph, but with the cosmological time limit slightly increased to include T1. The reason for displaying the limit T1 is to emphasize the period when the rate of change of the Hubble constant in the time domain was negative. This means that from the instant of the Big Bang at T alpha to T1, cosmological expansion was decelerating, as the SMOC expects. Then at T1, cosmological expansion commenced accelerating, and the rate of change of the Hubble constant in the time domain was positive. So then, comparing graphical plot 5 with graphical plot 6, do we have some sort of conflict with respect to the commencement of cosmological acceleration? In other words, does the event at T alpha Q conflict with the event at T1? The short answer is no. These two solutions are not in conflict with each other. Let me explain. First up, this situation forms part of the cosmological acceleration problem we are investigating. So let's step back and look at the mathematical facts presented. On the left-hand side of the screen, we see that the deceleration parameter crosses the x-axis at T alpha Q. But what does this physically mean? Well, in the standard model of cosmology, the experimental observation of the deceleration parameter is a measurement relating to the movement of baryonic matter, such as type 1a supernovae. Thus, the deceleration parameter x-axis crossover point appearing in graphical plot 5 relates to the change in acceleration of baryonic matter, whereas the rate of change of the Hubble constant in the time domain changing sign at T1, as appears in graphical plot 6, relates to the instant when the expansion of cosmological spacetime commenced accelerating. In other words, cosmological spacetime and the baryonic matter it contains commenced accelerating at different instances in time. Thus, during the primordial epoch, the cosmological expansion of baryonic matter transitioned from accelerating to decelerating at T alpha Q. Shortly after, the cosmological expansion of spacetime transitioned from decelerating to accelerating at T1. In other words, the cosmological expansion of baryonic matter and spacetime transitioned from negative to positive at different instances in cosmological time during the cosmological inflationary period. It is important to remember that the cosmological inflationary period is required to exist in the standard model of cosmology and accounts for the rapid and exponential expansion of the spacetime fabric independently of the baryonic matter. Therefore, our cosmological acceleration postulate presented on this slide is entirely consistent with the standard model of cosmology. What we have achieved on this slide is the potential identification of the origin of the Hubble tension, that is, due to the change in sign of the deceleration parameter at T alpha Q and the change in sign of dH to T at T1. However, let's now execute a quick revision of the cosmic acceleration problem which we have discussed and considered in previous episodes. This is an illustration of cosmological history which we have presented in multiple previous episodes, which includes a detailed account of the cosmological inflationary period. We'll deep dive into this illustration momentarily, but we can summarize the history of the cosmos by outlining 14 key events. The 14th event is a general reference to the distant future, and the 13th event refers to the present epoch. So between the Big Bang and now, we have identified 12 key cosmological events. To begin with, we identify the start and end of the cosmological inflationary period. You can see that cosmological inflation started at t equals 0 and finished by 2t phi rho, that is, when the universe was about 10 to the minus 23 seconds old. Our estimate is slightly longer than the standard model of cosmology, which estimates the cosmological inflationary period to have finished by approximately 10 to the minus 35 seconds. Let's now walk through the illustration. The first key event was the Big Bang, and it occurred at T alpha. At this instant, the cosmological temperature was 0 Kelvin, and the magnitude of the Hubble constant was approximately 10 to the 61 kilometers per second per megaparsec. The second key event occurred at root 2 T alpha. This is when the cosmological constant transitioned from being positive to negative. At this instant, the cosmological constant and the dark energy density parameter equaled 0. The third key event was the instant when cosmological acceleration began, represented by T1. At this instant, the cosmic microwave background radiation was at its maximum value of 10 to the 31 Kelvin, and the Hubble constant decreased from its Big Bang magnitude of 10 to the 61 kilometers per second per megaparsec to 0, but only for an instant. The instant when the Hubble constant was 0 is the instant when cosmological acceleration began. By the time the universe was 10 to the minus 42 seconds old at T2, the Hubble constant had increased from 0 to approximately 10 to the 60 kilometers per second per megaparsec. So this means that for an instant in time, the universe stopped expanding, then started expanding again. Although it had stopped expanding, it was continuing to inflate. An analogy to the behaviour of the Hubble constant I have just described might be a ball thrown into the air. At the top of its travel, the ball's velocity is 0, but it continues to experience constant acceleration. Therefore, the velocity of the ball is analogous to the Hubble constant, and our constant gravitational acceleration environment is analogous to the cosmological inflation environment. Now that we have looked at cosmological inflation in some detail, we are going to scrutinise the 8th, 9th and 10th events. These events relate to standard model of cosmology estimates for the commencement of cosmological acceleration. To cut a long story short, the standard model of cosmology is in conflict with itself, and from this we have identified what we have termed to be the cosmic acceleration problem. Let's now do a deep dive into it. On the previous slide, we saw that the 8th, 9th and 10th cosmological events were the basis of a standard model of cosmology issue termed the cosmic acceleration problem. The particle data group assert that cosmological acceleration commenced at approximately 7.7 billion years. However, the US Department of Energy assert that the actual figure is approximately 9 billion years, and Fermilab assert a value of approximately 10 billion years. So these three authoritative references disagree with each other. The reason this conflict has occurred is because none of these standard model of cosmology solutions are constrained by the cosmic microwave background radiation. The evidence for this is displayed by the calculated values of cosmological temperature. All three events are attached to distinctly different thermal conditions. So, it appears that these distinguished institutions have observed cosmological evidence of something, but may have misinterpreted their results. We will come back to that in a moment, but for now let's inspect the EGM solution. First off, the EGM solution is constrained to the cosmic microwave background radiation. Second, it commenced during the cosmological inflationary period. This makes much more sense than the standard model of cosmology claim that all points in cosmological 4D spacetime simultaneously commenced accelerating their expansion, for no apparent reason. The EGM construct has analysed these standard model of cosmology results and determined that the particle data group conclusion actually relates to the instant when the cosmological constant and the dark energy density parameter equaled 0. In contrast, the US Department of Energy solution actually relates to the cosmological instant when the dark energy density parameter equaled the deceleration parameter. However, the 2008 Fermilab solution correctly identifies when the deceleration parameter equaled 0, that is, the instant when it transitioned from being positive to negative. Let's now inspect the EGM solution in detail. This is what the standard model of cosmology would look like if it were cosmic microwave background radiation constrained. This is a graph of dH to t, that is, the rate of change of the Hubble constant in the time domain. You can see in region B that the Hubble gradient is negative from the instant of the Big Bang at T alpha to the instant of maximum cosmological temperature at T1. This region of negative Hubble gradient means that the universe was decelerating between T alpha and T1. However, at precisely T1, it stopped decelerating and started accelerating. The instant of maximal Hubble constant is marked by T2. This instant coincides with the instant of maximum cosmological acceleration. So, the expansion of the universe started accelerating at T1, with its peak value of acceleration at T2. From T2 to the present epoch, the universe continues to accelerate, but it is accelerating at a slower rate now than it did at T2. So, you can think of it like this. The universe is currently accelerating, but the rate of acceleration is decreasing asymptotically to 0. This means that the universe will achieve a constant speed of expansion after an infinite amount of time when the acceleration reaches 0. One of the most significant messages to receive from this slide is that the cosmological acceleration was derived organically within the EGM construct and did not require any band-aid fixes or inclusions. By following the EGM method of solution, the standard model of cosmology is not required to execute any adjustments in order to accommodate observational data. Okay, let's now tie everything together. The cosmic acceleration problem originates from 3 authoritative sources associated with the standard model of cosmology. We saw that the Particle Data Group, the US Department of Energy, and Fermilab attribute the commencement of cosmological acceleration to different instances in time. The Particle Data Group assert that it began at a cosmological age of approximately 7.7 billion years. The US Department of Energy assert that it began at a cosmological age of approximately 9 billion years, and Fermilab assert that it began at a cosmological age of approximately 10 billion years. All 3 estimates can't be simultaneously correct with respect to cosmological acceleration, so which one is correct? Well, in order to determine the answer to this question, we utilize the EGM construct. Firstly, we assert that the Particle Data Group estimate actually relates to the cosmological instant when the cosmological constant equaled 0, at a cosmological age of approximately 7.28 billion years. So the value of 7.7 appearing on screen becomes 7.28. Secondly, we assert that the US Department of Energy estimate actually relates to the cosmological instant when the dark energy density parameter equaled the deceleration parameter at a cosmological age of approximately 8.46 billion years. So the value of 9 appearing on screen becomes 8.46. Thirdly, we assert that the Fermilab estimate of approximately 10 billion years actually relates to the cosmological instant when the deceleration parameter equaled 0, at a cosmological age of approximately 9.63 billion years. So the value of 10 appearing on screen becomes 9.63. This also means that of the 3 standard model of cosmology estimates specified, the correct one relating to the commencement of cosmological acceleration is the Fermilab estimate. Thus, we have resolved the portion of the cosmic acceleration problem residing in the observational domain. However, the portion of the cosmic acceleration problem residing in the theoretical domain is a little trickier to deal with. We saw on a previous slide that the behavior of the standard model of cosmology deceleration parameter in the early moments of the universe could only be revealed via the EGM construct. In other words, the standard model of cosmology lacks the maturity for an end-to-end articulation of the deceleration parameter, so to fill in the blanks, the EGM construct was utilized. As you can see on screen, the process flow indicates that the observational data associated with the deceleration parameter comes from the cosmic distance ladder Hubble constant, which is determined by the direct observation of baryonic matter.
The key events specify that the deceleration parameter was negative valued from the instant of the Big Bang at T alpha to T alpha Q. It then became positive valued until TQ. At TQ, it transitioned from positive to negative valued, indicating that the universe is currently accelerating. And, as indicated, cosmological acceleration diminishes to zero after an infinite amount of time, at which point the rate of cosmological expansion will be constant. However, the behaviour of baryonic matter is not the end of our purview. We also have the cosmic microwave background radiation to consider. When we do this observationally, we see that the measurement of the Hubble constant differs significantly. In fact, it gives rise to a phenomenon termed the Hubble tension. Hence, we propose that the cosmic acceleration problem is composed of 4 parts. The first part involves the acceleration of baryonic matter in the primordial epoch. The second part involves the acceleration of the space-time manifold in the primordial epoch. The third part involves the acceleration of baryonic matter in the present epoch, and the fourth part involves the acceleration of the space-time manifold in the present epoch. Okay, let's now summarise what we have learned. On our journey, we have learned the following 6 points. Number 1. The standard model of cosmology is in conflict with itself because Particle Data Group, US Department of Energy and Fermilab estimates for the commencement of cosmic acceleration are in conflict with each other. Number 2. Baryonic matter commenced cosmic acceleration at a different instance to the commencement of space-time manifold cosmic acceleration. Number 3. Baryonic matter experienced 2 instances of change in cosmic acceleration. The most recent instance results in the cosmic acceleration we measure today via the cosmic distance ladder Hubble constant h0. Number 4. The space-time manifold has experienced only 1 instance of change in cosmic acceleration. In other words, the space-time manifold commenced cosmic acceleration during the cosmic inflationary period and is revealed by the measurement of the power spectrum Hubble constant h phi. Number 5. The origin of the Hubble tension is tied to the origin of the cosmic acceleration problem. However, the influence of cosmic acceleration is not the only contribution to the Hubble tension. Other contributions exist, which have been discussed in previous episodes. Number 6. Our proposition of baryonic matter and the space-time manifold experiencing different manifestations of cosmic acceleration is evident in the standard model of cosmology need for the existence of the cosmic inflationary period, that is, the period when the cosmic space-time manifold expanded at many times greater than the speed of light c. Thus, a precedent for our proposition already exists within the standard model of cosmology.